Today, we're going to talk about a very popular topic recently, the design of dual gyroscopes. We'll start by analyzing the Betaflight source code to understand why dual gyroscopes were introduced in the first place. And we'll also discuss the real-world issues that appear when dual gyros are implemented in hardware. Let's first take a look at the part of the Betaflight source code that handles dual gyroscopes. As you can see, Betaflight simply sums up the readings from all gyrons, and then calculates an arithmetic mean. It's really that simple. If you have the gyros, it just takes the average of the two. And if you have 3 gyros, it averages all 3 of them. So what does this averaging actually give us? Let's look at this from a mathematical perspective, and briefly review something we learned back in middle school. That is, expectation, variance, and standard deviation. If you have the gyros on the same PCB, their expected values are essentially the same. You can treat them as coming from the same distribution. In an ideal situation, if the 2 gyros are independent and identically distributed, the expected value remains unchanged. However, the variance is reduced to half of the original value, and the standard deviation becomes the square root of 1/2, which is about 0.707 times the original. That means, if everything works as expected, the original white noise of the gyro can be reduced to about 70.7% of its original level. In other words, you get roughly a 30% noise reduction. This is the most fundamental idea behind Betaflight's dual gyro fusion. By the way, if we extend this idea further, for example, if your flight controller had 3 gyrons, for gyros, or even 100 gyros, the noise reduction would theoretically be 1 divided by the square root of n. Here, n represents the number of gyroscopes. But is reality really that perfect? In the next episode, I'll show you how harsh reality actually is.